when x is equal to 0. F prime of 0 is equal to negative 2. So that says that if I look at x is equal to 0, and I imagine a tangent line here, the slope of that tangent line is negative 2. When x is equal to 1, if I imagine a tangent line, well, that's right at the bottom of my parabola, and so my tangent line is actually a horizontal line that has a slope of 0. And if I walk, well, here's 1, 2, 3, 4, 5, 6, 7, 25. So I come down here to 25. Well, that graph is, first of all, through the roof. And second of all, it's extremely steep and has a slope of 48. Okay, so here's our picture. Now, I want to draw another picture directly below this because our derivative is in fact a function as well. So I'd like to graph that derivative function, and go ahead and graph that on your calculator, and I will attempt to graph it up here, and you guys can fix it for me afterwards. We're going to graph y is equal to f prime of x. Now, f prime of x is 2x minus 2. And so we have a y-intercept of negative 2, and we have an x-intercept of 1. And so hopefully the picture that you get when you graph 2x minus 2 looks something like this. I did a better job of this one? Yeah. Okay, great, thank you. Okay, so I want you to take a look at both of these pictures as they're drawn up on the board. And some things that you'll notice about these pictures. When we have a flat spot on our original function f, the height of our f prime graph is 0. When our original function is increasing, is moving uphill, our f prime graph, the height of our f prime graph, is positive. It's above the x-axis. And when our original function is moving downhill, when our original function is decreasing, our f prime function is below the x-axis. So, f increasing corresponds to f prime being above the x-axis. Because f has a positive slope, so our graph describing slope had better be positive. When our original function f is decreasing, meaning moving downhill, our f prime function is below the x-axis. And when our original function f is flat, this corresponds to our derivative function touching the x-axis. All right, so we just made a switch here. At the beginning of class and in prior classes, we talked about the derivative as a number describing the slope of a function at a given value, a given x number. And what we've just done is switched over from a slope at a particular number to, we have an entire function that describes the slope of our original function for any x value you want. And so rather than thinking of a derivative as the slope at a particular point, we want to sort of think of a derivative as a global idea. We want to think of a derivative as a function of x. And so we write this, and the book makes a huge distinction about the derivative at a particular x value versus the derivative as a function of x. And the difference is we're looking at the slope here versus we're looking at sort of the trend of the slopes overall. And so we have this definition which says f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And this definition is saying that we are defining a function of x. So f prime is some function of x, and this function of x is defined exactly in this limiting way. So the little thought bubble on here is we are thinking of f prime as a function of x. And so we have an entire graph that corresponds to f prime, and that graph is related to the graph of our original function f. Okay, so it's time to take a break, and when you come back from your 10-minute break, then we're going to think more about this idea of the derivative being a function related to our original picture of our function. So we'll talk more about that.